This microchip can take up to 26 weeks to make. In its as many as 100 layers, billions of transistors are packed into an area about the size of a fingernail. They're the brains behind almost everything we use in our increasingly electronic world. Here's how these complex, tiny devices are made. The process begins with silicon-rich sand. Why silicon? Silicon is a semiconductor. It's the sweet spot between an insulator and a pure conductor. That means its properties such as its conductivity can be altered by adding impurities or doping to meet the needs of different electronic devices. This also allows us to control the electrical signals that pass through. Silicon is also abundant. It's one of the 10 most common elements found on Earth. But much of the silicon found in the wild is chemically bound to oxygen, so the two elements must be separated. The sand is combined with carbon and melted in crucibles to produce carbon monoxide and 99% pure silicon. After further processing, ultra-pure silicon is produced. Next, a seed crystal is placed in contact with molten silicon. As the seed crystal is slowly pulled away, silicon atoms are deposited on the bottom surface. The result is a large cylindrical boule, or a single crystal ingot of pure silicon. The boule is then thinly sliced into wafers. Silicon wafers typically have diameters of 1 to 12 inches, with the most state-of-the-art facilities being able to produce wafers up to 18 inches in diameter. Bigger wafers are, of course, able to yield more microchips. Once the silicon wafers are cut, the production process begins in full. Microchips are made in extremely sterile conditions, free from contaminants such as dust. If even just one particle of dust makes its way onto a silicon wafer, the entire batch is at risk of being ruined. This would derail a process that can take an average of 12 weeks. The first step of the production process is deposition. A thin, non-conducting layer of silicon dioxide is grown or deposited on the surface of the wafer. Then the silicon wafer is prepared for lithography by coating it with photosensitive and light-resistant materials. The next step is very critical: exposure. The prepared silicon wafers enter a lithography machine and are exposed to UV light passed through a reticle containing the chip's blueprint. The areas exposed to light are hardened, while unexposed areas are then etched away by hot gases to leave a three-dimensional microchip. The electrical conductivity of different parts of the chip can also be altered by doping them with chemicals under heat and pressure. This process can be repeated hundreds of times for the same chip, producing a more complex integrated circuit at each step. To create conducting paths between the components, a thin layer of metal, such as aluminum, is overlaid onto the chip, and the etching process is used to remove everything except the thin conducting pathways. Several layers of conductors separated by glass insulators can be laid down. Each chip on the wafer is then tested for performance before it's separated from other chips on the wafer by a saw. Since microchips are essentially circuits built on an incredibly small scale, they have a basic set of components. Capacitors can temporarily store an electrical charge. Resistors help control the electrical current. Transistors can either amplify or switch the electrical signals passing through. For more advanced chips, like those found on high-end graphics cards, there can be upwards of 28 billion transistors on board. More transistors on microchips allow them to send out more instructions, increasing the computational power. Moore's law predicts that computer chip manufacturing would advance at a steady rate, allowing transistor counts to double every 2 years. Based on the sheer power of the technology we use on a day-to-day basis, this decades-old prediction seems to still be mostly true. Manufacturers have been shrinking down their transistor sizes to fit more onto chips. Each breakthrough in transistor size has allowed the production of more powerful chips for our phones, computers, and gaming consoles. In recent years, they've gotten each transistor down to as small as 8 times 10 to the power of -8 inches in diameter, allowing an amazing 50 billion transistors to be crammed onto a single chip. Manufacturing microchips is truly one of our most complex feats. And yet, innovations are happening